Hey everyone. So I wanted to do a quick video as we're getting into Bernoulli's equation. Trying out some new tech here. So got a desktop document cam. Hopefully this will allow me to do a little bit better. There's still kind of a delay to it, so we'll do our best. I think this has slightly less delay than doing the connection through the tablet over the internet or over the wireless network. So I'm gonna try doing this way for this video. Let me know if it's better or worse, and we'll kind of switch it up as kind of progress here. All right, but I wanted to go over Bernoulli's equation. So last Friday during our online lab that we looked at, we went over our continuity equation, right? This is the simplified continuity equation without our density 1, density 2, since both sides of, say, our flow, water going through, say, this section, part 1, is the same as the water going through this part, so the density hasn't changed. Hence, we can cancel both those densities out, and we're left with just our area 1 times velocity 1 is equal to area 2 times velocity 2. So this is our continuity equation. Hopefully that made sense last week. If not, let me know and we can go over that. Review that this week during our online lab. For Bernoulli's equation is basically our next step that is very similar to our continuity equation. So what we're saying is we don't lose any energy from going from this point, going into this point, then coming out of this point. So our energy stays the same. So this is what they're showing here, and this is what the basis of Bernoulli's equation is built off of. So here we have our simplified energy equation, and we have 3 different types of energy that we could get here. So we have our flow energy, fluid energy, potential energy, and then a kinetic energy. Believe that. Just make sure. Fe. I'm trying to remember. Yeah, flow energy. So that just double checking. That's on the previous page here. So if you're wondering where those come from and what's derived of those, we have them here. So you can't remember what was PE equal to. That's this page here would be a good indicator of what to use. So 127, it shows us what types of energy are going to be involved in this equation. So potential energy, it's going to be, well, like dropping a pencil or anything. So we have potential energy before we actually drop it, right? So what we're actually seeing here is how much weight and how high up is that. So that's basically our potential energy equation. So weight times a distance and height. Kinetic energy, so that's how much moving energy we have, right? So potential to kinetic is typically the way things work, but in this case we have multiple different types of energy here. Since we have pressure, it's built up its potential, right? Kinetic energy is really derived from our flow. So how fast our flow is kind of depicts how much energy is actually going through the system. So we have our weight times velocity squared over 2 times our gravity constant. And this is going to be our kinetic energy equation. Finally, the third form is just our flow energy. So here we have pressure divided by specific weight. All gets multiplied by our weight. So this is basically the 3 equations that we're going to be looking from. And you're probably thinking, well, what constitutes as weight? Well, weight is shown here. So we have weight is equal to specific weight times the volume So how much volume we have flowing through there. So this is where we get specific weight for that, and this is how these equations are derived. Moving on to how this gets plugged into Bernoulli's equation. So Bernoulli basically stated this simple fact right here. So energy going into the system equals the energy going out of the system. So conservation of energy, so Bernoulli's using that conservation of energy as a basis for his equation. So here we see that E1, energy going in, is our flow energy plus our potential energy plus our kinetic energy. And same with E2, except for this is at point 2 in our circuit, or pipe. So we have point 1 and point 2. And what we're going to find out is as these areas change, well, flow rates essentially going to stay the same, but what we'll see is pressures will change. Velocities will change, but as far as flow rates, which we saw last week, is our continuity equation. And this is where a lot of these problems start off. So basically they say flow 1, which is area times velocity, is equal to Q2, or flow rate 2, area 2 times velocity 2. So that's our continuity equation, right? So we have our same flow rate, and then what we can do is we can figure out, well, what is the change in our velocities? Then we come into this equation down here, and then we can plug in our velocities, and usually we're given, say, one or the other pressures, height in the fluid. A lot of times we'll see small changes. If there's an elevation change like this one, yes, there's going to be a z height here. Otherwise, if it's completely horizontal, there won't be any z change. So other than that, that's Bernoulli's equation. So when everything gets simplified, Bernoulli's equation basically gets simplified to this equation 6-9 right here. And this is a rather simplified equation, so we can solve for our pressures, our velocities at a certain part of a pipe, or z height for, say, a given pressure that we want in a certain portion of the pipe. So that's Bernoulli's equation right there. I'm going to go on to do an example problem. I'm just going to go through this one here, 6.9. So this is using 6.7 as an example. So that's going to be this figure right here. And they want to basically solve for, well, let's see. So we're going to solve for probably pressures, I would imagine, different pressures in the system. So here we want to see, so this is typically how the problems will basically work with homeworks in this section for Bernoulli's equation. So we're going to use that figure I just showed there. Water is at 10 degrees Celsius. It's flowing from section 1 to section 2, so it's flowing upward, which is 25 millimeters in diameter. The gauge pressure is 345 kilopascals, and the velocity of flow is 3 meters per second. At section 2 of the pipe, which is 50 millimeters in diameter, is 2 meters above section 1, so there's our z height right there. And we're going to assume there's no energy loss in the system, so we're going to calculate pressure 2. The light's kind of reflecting pretty badly. So we want pressure 2. So what the example problem goes through and shows is, well, what are we given? So we're given that D1 is 25 millimeters, so our diameter on pipe, first part of the pipe there is 25 millimeters. D2, our flow out essentially is going to have our 50 millimeters. So flow in, 25 millimeters, flow out, 50 millimeters. Velocity at 1 we're given. So it's 3 meters per second. And we're given pressure at 0.1. We're given that Z height. So those are our knowns. Now, next part of the process is really looking at Bernoulli's equation itself. So Bernoulli's equation looks like this. And what I like to do anyways, is really look at, well, what do we know of the system? What can we plug in here? If there's anything that says 0, so for instance, if Z height was 0, we could go through and basically cancel that out so we wouldn't have any Z's. In this case, our Z height is 2 meters, so we can't necessarily do that. Let's see what else we got. So we have velocity 1. Let's see, trying to do this while looking at the screen. V1 squared. And we know pressure 1 here. Let's see what else. We have the Z heights. Gravity is constant, right? So we do know our gravities. Something we don't necessarily know is V2, so that's not given, and P2, and that's not given. So there's the two unknowns, and that means we need the two equations. So what they go through is that they're solving for, since we're ultimately solving for pressure 2, they set up the equation and then solve for P2. So that's what they're starting with. Basically, they're going to then try to figure out, all right, so once we get this equation, let's plug in our known values. So at this point, we're given water is at 10 degrees Celsius, so we know our specific weight. Pressure 1, we know is 345 kilopascals. Again, we know our specific weight will be the same. Z1 minus our Z2. You can see we simplify this here, and we get our height. V1 we have, and we just need to find V2. So looking at that, well, how do we solve for V2 now, right? Well, remember we have the continuity equation. So we want to use this to solve for V2. So we end up looking at this. V2 is equal to, well, manipulating this equation, we get V1 is times A1 divided by A2. Once we have that V2, we can plug that right into this part of the equation, and then solve for the rest of the problem. So this right here goes to 2 meters. All right, V1, we saw that as our 3 meters per second. V2, so V2 over here, they go through and equate. So V2, that equation, we need to know our areas, A1 and A2. And you can use that trick we talked about in last class, how the pi's will end up canceling, the 4's end up canceling, and really you can do a ratio of your diameters squared. Make sure to square those areas or diameters as a ratio, or that ratio won't work out. Right, you can do a simple test, right? So if you did, say, D1 was 1, D2 was 2, well, if we were doing that D squared of 1 divided by D squared of 2, well, it would give us a quarter, right? Well, if we do not square that, it gives us a half. So make sure to square those values if you're going to do it that way. Otherwise, just plan on solving for areas and using, this method here. Nothing wrong with that. All right, so V2 is equal to our V1, which we said was 3 meters per second. And then we wanted to multiply this by our area, ratio and area, right? This ends up being, well, A1 was 491, A2, we opened up to, what, 50 millimeters that was. So that gives us 196. We get that ratio there, multiply that by our initial velocity, and we get that basically this is going to get slowed down. And thinking about how the pipe is actually set up, so try not to lag this out too much. But thinking about how this pipe looks, we have a smaller section here. And what we said with continuity equation is that we get the same flow rate here as we would here. Well, thinking about this, if it, just thinking gallons per minute, it would take the same amount of time to flow through this section as it does this section, right? So 1 gallon per minute flowing through this section has to go much faster, or at least 0.25 in this case. Or wait, actually, no, it went from 3 meters per second in this section to 0.75 meters per second in this section. So it opened up a wider area, meaning, well, if it gets the same flow rate, that velocity has to decrease. Smaller area means velocity has to increase to keep that same flow rate as a larger area section. So the interesting thing with Bernoulli's equation is this also results in a pressure drop. So we solve for that velocity, get our velocity at 2. Now that we see that we have this velocity drop, what is our pressure drop going to be? So this is where they go through and then plug it into that initial equation I was kind of writing numbers next to over here. So that was, we mentioned that was 3 meters per second. That was our 2 meter height. So this whole thing here is 2 meters. This was our 0.75 meters per second. Gravity constant, right? We have gravity constant as 9.81 meters per second squared. And then our pressure one, we said, was given, and that was 345 kilopascals, right? So you're just plugging everything in. That specific weight of water at 10 degrees Celsius, that's something you're going to want to pull from the back of the book. This gives it down here. This is our specific weight here. It ends up being the same as our 4 degrees Celsius. It doesn't necessarily change that quickly. So then you would plug in your 9.81 kilonewtons per meters cubed. So that gets all pushed in there. So that's basically what this next step of the example problem is doing, is just plugging in numbers. To plug in the numbers, solve for P2. And they get pressure 2 is at 329.6 kilopascals. So notice how we got a pressure drop there. So velocity decreased, and we ended up losing some pressure. So area increases, velocity dropped, and we also get this resulting pressure drop of 329.6 kilopascals from our 345 kilopascals. So is that about less than 20 kilopascals, but it is a drop. So basically this just goes to state the pressure 2 is a gauge pressure. So it's stating that this is at gauge. So technically if we were doing this in absolute, we would have to add that atmospheric pressure, right, which is 101 kilopascals thereabout. So this is just gauge pressure. So it's usually good to state, especially if you're doing it for your scientific application. Sometimes you give pressure, and if it's given to a scientist, they might automatically assume atmospheric or absolute. So just make that. Usually, it's good to say kPa, and sometimes you can write gauge in parentheses, or KPA. I think for English units is PSIG. Personally, I would just write gauge so people don't get confused. Sometimes you don't always see that. You typically just see PSI or KPA. So I'd just do parentheses and write gauge or absolute, depending on which one you're in. But that's about the gist of Bernoulli's equation there. I'm going to be doing another example for 6.10 to walk through that one. I think it's 6.10. I'm going to do that in another video, so this one doesn't get too long. Alright, so I'll be making another one, post that up here soon. Alright, but please ask questions, guys. I'll do my best in answering them, maybe put up another video showing a different example problem. This one I just wanted to work through the example problem. I will be doing some by hand. I just figured I'll walk through this one for this video. But please, again, let me know if you have questions, and hope everybody's staying safe and staying healthy. Alright, talk at you later, guys.